Here's a differential equation. 3y prime equals x cubed minus 12xy. I look at it and it's first order because of the y prime. No initial condition is given, so I don't have to find the c, the one c that I would get because I'm solving a first order. I don't have to find that. How do I solve this? Oh, it's first order and it's linear. So I'm going to put it into that form. The first thing I'm going to do then is move the minus 12xy over to the other side. What I'm trying to do is put it into the form y prime plus py equals q. So it's strictly y prime, so I can't have any numbers in front of here, or I have to have a 1. So I'm going to divide the whole equation through by 3. Divide everything by 3. 12 divided by 3 is 4, and that's going to put a x cubed divided by 3. I'm just going to write it as a third. So to get from this stage to this stage, I moved the 12xy over, so it became a plus 12y, and divided everything by 3. The dividing by 3 was so that it could be put into the proper form, y prime plus py equals q. So now it's in the standard first order linear form. I'm going to get the integrating factor. The integrating factor u is equal to e to the integrate p, so e to the integrate 4x. That's going to be e to the 2x squared when I integrate the 4x with respect to x. Don't need a plus c on that. Now my integrating factor, I'm going to multiply all three sides through by that integrating factor. Take my differential equation, my first order differential equation, first order linear differential equation that's in standard form, y prime plus py equals q, and I multiply all three sides through by that integrating factor. Now I'm going to integrate both sides. I'm going to integrate both sides with respect to x. Integrating the left-hand side, those two pieces always integrate to be y times the integrating factor. That's why we chose the integrating factor in that form. Where do these two pieces go? Those two pieces, when they get integrated, become this one piece. Because if I do the opposite of integration, if I do differentiation, I would be differentiating this y integrating factor by product rule. So it'd be derivative of the first, the derivative of y is y prime, leave the second alone, plus leave the y alone, and this would be the derivative of the integrating factor. So where did these two pieces go? They get integrated into this one piece. Now I have to integrate both sides. I haven't looked at this right-hand side. It's not something that I can just integrate off the top of my head. So let's leave it separate and let's solve it now. But at this point, it's just a calculus problem. So I need to integrate this side with respect to x. I'm going to do integration by parts on this one. I need a piece to, so when I do integration by parts, my parts are f and g. Sometimes you would learn it with u's and dv's. I need one part to differentiate and one part to integrate. So let me put the integrate part first because that's going to kind of govern what's going on here. So if I choose to integrate the e to the 2x squared, I can't do that unless I have one of these x's. I have three x's. That leaves me with x squared on this side. This third, it's got to go somewhere. Let's just put it on the f side. So now I've split my integral into the two parts. One part that I can integrate and one part that I can differentiate. I guess the whole trick of doing integration by parts with this piece is to leave one of those x's there. Now, when I differentiate the f part, I'm just going to get 2/3 x. And when I integrate the g part, I'm going to get, okay, I could do that by substitution, but let's do this more by inspection. So if I were to differentiate e to the 2x squared, that would be e to the 2x squared times 4x. Oh yeah, that's what I got up here, right? But I don't have the 4 in front. So I'm going to put a quarter, and now when I differentiate this g piece, I get this g prime piece. So now we can go back up to and do our integral. Integration by parts is supposed to be equal to f times g minus the integral of the two pieces I made. So the two pieces I made are this piece and this piece. So you might do integration by parts differently, or with you're not doing it differently, you're just using different symbols. But integration by parts, that's how it sets up. Let's clean some things up. This 4 on the bottom and a quarter, I can just multiply that together and make that a 12. This 2 over 12, I'm just going to take that to the outside as a sixth. That's going to get rid of all those fractions, right? The 2 cancels with the 4. And now, now this I can integrate because I already integrated it. That's just going to be a quarter e to the 2x squared. All right, now I'm just going to integrate that, which I already did. It's this. So this integral becomes done. Oh, and now's the part where I tack on a plus c, and I guess the 1/6 times the quarter, let's make that a 24th. And I'm done as far as there's the implicit solution. If I wanted the explicit solution, I would take this whole piece and I want to multiply through by e to the minus 2x squared. So I'm going to cancel that e to the 2x squared off all sides. So it leaves there, it leaves there, it leaves there, and then it gets tacked on here as a minus. So implicit solution, explicit solution. Now, this is just a caution. It makes a difference when I put the c on. I have to put the c on, the constant, at the very stage when I integrate both parts. If I try and solve for explicit and then tack it on the end, I'll miss that e to the minus 2x squared. Anyway, we had a first order linear and we solved it. This, however long this video is, 6 minutes of it was calculus, right? Just solving this integral was the calculus part. The differential equations part was just getting into that form, knowing to multiply by the integrating factor, knowing that it's a first order linear, and we have a method for that.